Hey everybody, welcome back to Algebra 2 Online. So the plan for today is to start our really important unit on trigonometry. So it's literally in the name of the course, so probably a good clue that this topic is really important. And honestly, it's the most important thing that I'll be teaching you all year long. It's just one of these topics that just continuously shows up in math and science, and if you don't have a good handle on trigonometry, then it makes a lot of things a lot harder. You learned in geometry a bit of trig, and you basically really learned this SOHCAHTOA thing, and I'll actually do a problem kind of related to that. It's kind of related to problems like this, where it's like you calculate these like angles of elevation or angles of depression. But there's so much other stuff to trig. This is something called the unit circle, which is like one of the really important things that we talk about in this course. You learn about in Algebra 2 graphs of sine functions, cosine functions, tangent functions. There's other ones. There's something called cosecant and secant and cotangent. And we'll talk about all those different graphs of trig functions. But they just have an insane amount of applications all over the place. If you don't know this, light is actually a wave. So light moves just like a wave function does. And the wavelength dictates actually this spectrum thing that we talk about. And there's a little window of visible light, but there's all sorts of things like radio waves that are happening that we can't see. And on the other end, really kind of more rapid waves are like X-rays and ultraviolet and stuff like that. But there's stuff with wave functions in music. This is actually the graph, kind of got cut off here. This is literally the function of the chord A, C sharp, and E. This is A, C sharp, and E. And I did music theory when I was in high school, and you can actually connect math to that really easily if you know some trig. It's just used this is like what we call celestial mechanics, talking about orbits of planets, and it's insane how many places trigonometry shows up. So there's a lot of really important stuff I want to talk about in this unit. And I never have enough time to say everything I want, but you study a lot of this in pre-calc, again, just like a harder level, and then eventually in calc you even learn stuff more again, and it just kind of never goes away. You just keep adding and adding and adding to trig. And so if you get a really good base in like this stuff here, it's going to suit you really well going forward. So this is actually just kind of like our quick kind of review problem, like from geometry. So this is sort of what you're supposed to know coming into Algebra 2 in my book. Basically, you need to know SOHCAHTOA really well. And just as a quick review, this is just an acronym for the sine function is defined as the opposite over the hypotenuse, cosine is defined as the adjacent side over the hypotenuse, and tangent is the opposite over the adjacent. And what I'm talking about there is like in a right triangle, right? If this is my angle, all right, then the sine is the opposite side, right, over the hypotenuse, okay? The cosine of that angle in there is the adjacent, which really just short for next to side over the hypotenuse. And you might wonder, like, hypotenuse is also kind of next to adjacent, or next to the angle, the same way the adjacent side is. But this is an extra special side, so it gets an extra special name because that side is the one that is longest. So it's hypotenuse. And then tangent is the opposite over the adjacent. And so we can do problems like this if you know this stuff from geometry. So suppose a person on the ground looks up at me rock climbing, and they bust out their protractor to measure the angle they're looking up at me at. And they measure that angle in there is 57 degrees. So there's some angle looking up at me climbing that's 57 degrees. So here's the cliff, and this is me climbing there we go. That's as good of a picture as you're going to get. Here, just, there we go. Perfect. And then they also have an abnormally good sense of distance, and they know that they are exactly 1/2 of a mile from me, okay? The question that you can solve using what you know from geometry with this stuff is how high up the cliff am I, okay? So we want to know from this point to this point, how high up the cliff am I, right? And so in geometry, you kind of do these problems, and these are what we call, this would be called an angle of elevation, because like from the ground, we like elevate up 57 degrees. And so you kind of just think, okay, what relates this side and this angle, and this is in a right triangle, and it would be tangent, right? Opposite over adjacent is tangent, and so you can set up the problem, okay, tangent of 57 is equal to the unknown thing, the height there, right, over the 1/2 mile, so 0.5. And so then to solve for x, you just do 0.5 times tangent of 57, and that's technically an answer, but that's approximately 0.77 miles. So there you go. So that's what you kind of need to be comfy with from geometry. And I am going to be sort of assuming that we're good with that, because we're going to be moving on to a whole bunch of other kinds of stuff. And today I want to talk about specifically this idea of something called a rotational angle, all right? And this is not something that you probably would have studied in geometry. So when it comes to angles, there's actually 2 units that you commonly see. There's something called degrees, which we're kind of more used to, and then there's something called a radian. Okay, and I want you to think radius for that. There is going to be a connection between this unit and the radius, and we'll talk about that. But they're both useful. Okay, this one is really good for problems where you have like angles of elevation or depression, and so basically problems like this last one. So this is again an angle of elevation. Someone was looking up at me climbing. You can do angles of depression where you're looking like down from a balcony or something at someone down here. And so those kind of problems is where you really use degrees. Like I built a climbing wall in my friend's garage once, and to build the climbing wall, we basically we built a little piece of wood here, and then we had the wall coming out, and then there was another piece of wood, and this is kind of the roof, this is the floor. And so we needed to do some trig, and we actually did. He's an engineer, and I teach math, and so we're pretty good at this stuff. And so we calculated all sorts of things where we could calculate basically what this angle we wanted it to be off the ground, and we could calculate these angles in here, and all that sort of stuff is angles of elevation depression. Those are degree problems. There's another kind of thing where we deal with rotational angles. And when we deal with rotational angles, that's where you're going to use this thing called a radian. So rotational angles is where you really are going to use radians. You actually can use degrees. That's fine for rotational angles, but a lot of times we're going to use radians, okay? You might wonder, what is a rotational angle? Well, I'm going to try to just draw a picture to show the idea of it, okay? So I'm going to sketch these 2 angles, and I'm going to sketch them as rotational angles, okay? So let's do the positive one here first. So I'm going to do 400 degrees here. I'm going to do a negative 135 degrees here. So when we talk about rotational angles, we're talking about problems in the XY plane where we're rotating around and around and around and around and around. And we specifically follow the direction of the quadrant. So remember that quadrant 1 is here, 2 is here, 3 is here, 4 is here. And if you go in that direction, 1, 2, 3, 4, that's the positive direction. If you go 4, 3, 2, 1, so clockwise is actually negative, anti-clockwise is actually positive. A little weird, but it does follow the signs well. Like this should definitely be the first quadrant because positive, positive, right? Positive x is positive y. And this should be, if we started here and went this way, this should be quadrant 4. And you could argue like quadrant 4 could be up here, but that's just not how it is. This is how they did it. They said 1, 2, 3, 4. So 400 degrees, right, looks like this. You would literally start here. You start on the positive x, and you just rotate. You go around, that's 360, right? And if you go 140 more, right? If I did my math right, yeah, 140 more. If you end right there, that angle is what 400 degrees looks like. So a weird thing in a unit circle, in one of these kind of circular rotational problems, we haven't gotten unit circle yet, 400 degrees is actually equal to 140 degrees. Because you go around the full 360, you rotate around 360, and then you go a little more to get to your 400, right? And that's done by going 140 more than your 360. So in general, you can kind of think 400 is equal to 400 plus any multiple of 360. N is kind of like equal to 1, 2, 3, 4, so on and so on and so on. So this is what I mean by rotational angles. Just start here, rotate following the quadrants, that's a positive direction. If I want to do a negative angle, okay, you still always start here, but now you rotate in the anti-clockwise way. Clockwise. So 135 is going to take me to about right there. That is what negative 135 degrees looks like. That is where the angle would end. Negative, clockwise, positive is counterclockwise. So going this way. So that's rotational angles. And I'm going to make a connection now to that and talk about what this radian thing is, basically, a little more. So this is actually the definition of a radian, okay? But before I read that and get into that, I'm actually going to do this, okay? So I have 3 different circles, right? And for each circle below, I'm going to attempt to draw a rotational angle which starts at the standard position. So standard position is always kind of 3 o'clock in a sense. It's always, 3 o'clock. And I'm basically going to start from that standard position, and I'm just going to wrap the radius around the circle. So this is what I mean. So let's say that is the radius, roughly, right? I'm going to take this from the standard position. I'm going to wrap in the positive direction around, let's say that's about it, okay? That is roughly, the arc length there is equal to r as well. If I do another one, this little one has a little radius, so wrap it around, I don't know, it's about right there. We'll do one more here. What color? We'll do this. So here's the radius, right? Big radius, wrapped around, I don't know, let's say that's equal, r and r. So if you look at this, all of these, okay, if you kind of close off the angle, right? Those actually are all going to be the same, right? You could keep doing this for different circles, and you're always actually going to get the same measurement. That measurement is a radian. A radian is actually not equal to, I shouldn't really have that, about 57 degrees. 1 radian is the angle of the arc created by wrapping the radius of a circle around its circumference. So this is the radius, I wrap it around, and that is where I cut it, and that angle in there is roughly 57 degrees. Same thing here, roughly 57. Same thing here, roughly 57. It is a unit of measurement that is fixed no matter what circle you have. You would always get the same measurement, okay? And so I want to make a little connection to something else here. So we know there's 360 degrees in a full circle. If I divide that by 57, then that should be how many radians I have, roughly, right? So there are 6.32 radians, which we actually abbreviate rad, in a full circle. And one thing I recommend you doing is if you do 6.32 divided by 2, okay, if you do this, you're going to get 3.16, okay. Turns out, 3.16 is about pi, but I said that 1 radian was about 57. The amount I'm actually off there makes it so that a perfect circle is actually exactly 2 pi, and a half circle, which is like this would represent a half circle, right, is actually exactly pi. That is a super, super, super important fact that I want you all to know. So a full circle is represented by 360 degrees or 2 pi radians. A half circle then, right, would just be half of those things, right? We know that's either 180 degrees or pi radians. And you could keep going. You could do 90 degrees and da-da-da-da. But this is actually a really, really, really important fact. I can kind of show it a little bit better here, and that's kind of the purpose of this. We know that the circumference formula is C equals 2 pi r, right? Well, if r is 1, then this would be just 2 pi, right? This thing would just become 2 pi. So for a unit circle, the circumference is 2 pi, okay? That means there's like this natural proportion between 360 and 2 pi, right? So 360 is basically proportional to 2 pi. Or, you can think, okay, well, 180 is proportional to pi, or 90 is proportional to pi over 2. You could do 60 is proportional to pi over 3, right? Because 60 is a third of 180. So on and so on and so on and so on. There's this natural proportion, and this is basically how we're going to be able to convert between degrees and radians. It's going to give us a natural conversion tool, okay? So if you want to convert from degrees to radians, okay, because they're just units, so you should be able to convert between them, you multiply your degree. So, so all of these are proportional, right? And it gives us a natural way to convert between degrees and radians. If you want to take your degrees to radians, basically radians always have this pi in them somewhere. They technically don't have to. 6.32 can be thought of as radians, but we're very used to, usually seeing it with a pi in it. If there's a pi in the angle unit, then it's a radian, and if there's not, it's a degree. But this is basically your conversion. If you want to go degrees to radians, just multiply your degrees by pi over 180, which is basically like multiplying by a 1, right? Which shouldn't change anything because those are two that are proportional. If you want to go radians to degrees, you just multiply by 180 over pi, okay? Same thing, it's just still like multiplying by a 1. And the way I remember this is if I want the radians, I want the pi on top, which is like a radian thing. Anything with pi is radians. If I want the degrees, I multiply by 180 on top. But you just gotta like flip-flop which one's on top. and the one that's on top is telling you where you're going to end up, okay? So just to kind of show you over here, 75 degrees into radians would just be like 75 times pi over 180. And if you do that out, it's just 5/12 of pi. And truly, 5/12 is the fractional amount that 75 is of 180. If you do if you do 180 times 5/12, you get 75. It's just saying that, this degree is 5/12 of the way around half of a circle. That's the idea. This thing in radians, if I want to convert it into degrees, okay, you just flip it around. You go negative pi over 18. That radian measurement times 180 over pi. Basically what's happening is the pi's will cancel. And then you would get negative 10. You get negative 10 degrees. So when you look at this, if you want it in degrees, you can just always multiply by 180 over pi. And if you want the degrees in radians, just multiply by pi over 180. So one more thing I just want to do in this video is talk about actually how we can calculate area of a sector and arc length for both degrees and radian problems. So this actually relates to rotational angles because it's the area of like a sector could be defined by the rotational angle that gets you that sector, right? And same thing with arc length that we'll talk about here in a second. So area of a sector is like pretty intuitive formula. It's like, we know that the area of a circle is just pi r squared, right? But if we're talking about this sector of the circle, right, then we basically have a fractional amount of that, full 360. So the fractional amount is, in this problem, of course, 140 over 360. And so that's kind of the general template for area of a sector. You just, actually maybe as like a formula, this is actually the Greek letter theta, and theta, Theta, is typically the variable we use for an angle. And so this is sort of your formula for area of a sector given degrees. And so in this problem, if you do 140 over 360 pi, and then the radius is 3, if you go and plug that into a calculator, you get approximately 10.9956 inches, I guess. Whoops. Inches squared. So that's the area of that sector. The formula up here, if we wanted to do it in radians, right, it's pretty intuitive also that we would just switch the 360 to 2 pi, right? 360 is equivalent to 2 pi. So we would have theta over 2 pi and then times pi r squared. But here's something nice kind of happens. The pi's would cancel, right? And so it actually simplifies to theta over 2 r squared. So that is actually your formula if you were given a problem where this was a radian measurement. If this was a radian measurement, you'd use this. Here it's a degree though, so we used this formula, right? So that's kind of area of a sector. There's not too much to say there. Arc length is another thing that kind of relates to rotational angles and things, because we might be concerned with, you've got some rotational angle in here, and that is going to map out some sort of arc length, right? And it's just a proportion thing again. So the arc length is proportional to circumference, the same way that angle in there is proportional to 360 for degrees and 2 pi for radians, okay? So so in this case, right, L is typically actually the variable we use for this. We have circumference is 2 pi r, and then theta over 360. And if you solve for L, right, you could just multiply by 2 pi r. And so you have theta over 360 times 2 pi r. And so in this case, you get theta over 180 pi r. So that's your formula for arc length in degrees, okay? If you want to do radians, you would just have L over the circumference, 2 pi r formula, right, equals theta over 2 pi. And one thing you'll notice is that a lot of times in radians, things are a lot nicer. So here, when you solve for L, you get 2 pi r there. Notice the pi's cancel and the 2's cancel. So literally, arc length in radians is really, 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 really nice because all you do is you multiply two numbers. You multiply the angle. Yeah, that's it. Just multiply the angle times r. So now we can do kind of a problem like this. So this asks us to find the distance along an arc on the surface of Earth that subtends. It's like a word for kind of maps out a central angle of 7 minutes. And minutes are actually another unit for angles. 1 minute is 1/60th a degree. So think like a clock here. There's 60 minutes in an hour, and that is actually the conversion. 1/60th a degree is 1 minute. So pretty small thing, 1/60th a degree, okay? And if we were to, so the radius of Earth is 3,960 miles. I would personally use the arc length formula for radians because it's so much quicker. So you could do it in degrees, you're going to get the same thing, but I'm going to use arc length equals theta times r. And so we know r right there. We need to convert the 1/60th, okay? So 1/60th of a degree, if we want it in radians, we just multiply by pi over 180, okay, which is equal to pi over 10,800. And then you got it. You just pop the two things in. The arc length is going to be pi over 10,800 times by 3,960, which equals 1.1519. And so that is miles. So, this super small angle, right? Which is honestly like quite hard to even draw. But basically the idea is like in Earth here, you have this like insanely small little angle, okay? And it still maps out over a mile and I'm sure that is way more than 1/60th of a degree. But it still maps out way over a mile. Well, not way over, but over a mile on the surface of Earth. So the last thing I'm just going to say in this video, this is kind of where we're moving to, and this is going to be like our next video. This is a picture of what we call the unit circle, and there's tons of important things that have to do with the unit circle. There's going to be like all sorts of problems. I'm just going to be like, go back to your unit circle, go back to your unit circle. One of the things you might want to start thinking about is kind of the key angles in the unit circle. So 30 degrees right here, right? So always think about measuring from here, is equal to pi over 6. Those are just equivalent, right? That's kind of what 30 is. 45 is halfway between 0 and 90, right? That's pi over 4. 60 is pi over 3. 90 is pi over 2. And those just kind of keep going. Like 120 is a good one. 135, that's 90 plus 45, and like so on. 180, 270 is a really important one. These are ones that you kind of should start to feel like comfy with their location in terms of rotational angles. And remember, everything's always mapped out in that direction. So, when I say an angle of 300 or 5/3 of pi, okay, that is always measuring from here. This is what we call that standard position. So this is the standard position, that's where 300 or 5/3 pi is given that standard position. So I'll be saying a lot more about that stuff in the next video, but these rotational angles are really important to know for that next video.